Okay, so let me start talking about this example over here. Okay, so we ended up having two designs, two solutions. One solution is on the right side of this classroom, is a relatively conservative design. So the design is the idea is the following. So let me just the idea is if you have the wind speed, say WS, and the payload being the two axes. Okay, and they want to figure out one design that meets a certain wind speed percentile and a certain payload percentile, so that basically if the design works for that particular wind speed and the payload, then it'll work for more than 99 percentile of all the combinations. And the assumption here is that the payload and wind speed is independent. So why is it justifiable to say that the payload and wind speed are independent?
If I change my payload now, I'm not changing the wind speed outside.
Right. I mean,
the weather patterns by.
Right. So one is from like human demands, right? The other is from nature. I mean, it's hard to argue they are actually completely independent, because if the wind is higher, maybe somebody is going to order something wind related. I mean, so it's hard to argue they are exactly independent, but like you can, without data to support their dependence, it's basically reasonable to assume they are independent. Okay, so now if you assume they are independent, the question becomes to what percentile of the wind speed and what percentile of the payload, if this particular design works, it'll work for 99% of the combinations. Initially, the answer was 99% of this and 99% of this, right? Does that work? Why?
So it's 0.99 times 0.99 is less than 1.
Is less than 0.99, right? Yeah. So basically, the percentile of this quadrant of the design point is actually less than 0.99. So you have to make this, for example, 995 and 995 for that to work, right? That, of course, is relatively conservative, because if this point works, it probably means that the design works for an area like that, right? So basically, if the design works for that combination of payload and wind speed, it probably doesn't just work for that rectangular region. It works for a wider region than the rectangular region. So you are having an overly conservative design, but definitely it works. And if the cost of increasing the performance is not that high, that may be the way you want to go. Well, on this side of the classroom, we had a design that is more cost conscious, I would say, right? So they are really trying to figure out the design that is just good enough to satisfy the 99 percentile criterion. Okay, so the way they have been doing is trying to adopt the approach that if I have a design, if I have a particular design where I can evaluate the design, feasible or not, right, for any given wind speed and payload, then the idea is to actually exactly figure out this particular boundary. So if you can exactly figure out the boundary in the two-dimensional space of payload versus wind speed, then you can actually integrate, right? You can integrate from, for example, wind speed from 0 to infinity, d wind speed, all right? And then you can again integrate over from 0 to 1, because we know our maximum payload is 1 kilogram d payload. All right. And what's next? What do you actually integrate?
Joint PDF.
One is the joint PDF, which if you assume payload and wind speed are independent, the joint PDF is just equal to the product, right, of payload times the, let's say, payload PDF of wind speed. What else?
Need a step function.
Yeah, if I just look at that integral, it's guaranteed to be equal to 1, right? Because the integral of a PDF has to be equal to 1. That's kind of the definition of PDF. So I have to multiply by another function. In statistics, we call that an indicator function. I put it a big I. Okay, that big I is a function of payload and wind speed. It is equal to either 1 or 0, depending on if the design is feasible or infeasible for that particular combination of wind speed and payload. So, for example, if we have a very good simulation, we can evaluate that indicator function for every combination of payload and wind speed, right? Or if you have a good, if you're very good at doing, actually building the quadcopters to test, for every different payload and the wind speed, you can also just to see physically if it works or not, if your quadcopter can overcome that, that particular wind speed while carrying that payload. So either way, you can evaluate the 1 or 0 function. But the problem is that we have this integral here, right? So that means no matter if you do simulation experiment, you have to try out every possible combination of wind speed and payload. Right? So okay, so which is starting to become a problem, right? Even though now you are considering only 2 things that are uncertain. One is wind speed, one is payload. Still, you can design an experiment to figure that out, right? You can design an experiment, you can carry a payload, and you can just, in a wind tunnel, for example, increase the wind speed from 0 to until your quadcopter can no longer stay stationary anymore, and then you can figure out in which region of the wind speed it is 1, beyond that it is 0. You can still do that.